Welcome back, Semester 5 Industrial Engineering students, to today's explainer session. I'm absolutely thrilled to have you here. If you really want to be a top-tier industrial engineer, you've got to master the art of knowing exactly what material you need, how much you need, and, crucially, exactly when you need it. So today, we're diving deep into the absolute key to production planning, Material Requirement Planning, or MRP. Specifically, we're going to look at exactly how MRP schedules dependent demand to keep supply chains moving flawlessly. This isn't just some textbook theory. It is literally the operational heartbeat of every successful manufacturing plant on the planet. Let's get right into it.
Here's a quick look at our roadmap for today. We'll kick things off with the two categories of demand, and then tackle the dependent demand problem. From there, we'll introduce the MRP solution, dive into the crucial role of lot sizing, validate our capacity through CRP, and finally, wrap it all up with strategic, managerial decisions.
All right, Section 1, the two categories of demand. This is where we understand the real roots of inventory planning.
Classifying demand correctly is absolutely crucial. It's step one. If you get this wrong, you're setting yourself up for some fatal errors on the production floor. Everything starts with understanding where your demand is actually coming from. First, you have independent demand. This comes directly from the external market. Think of customers buying finished goods, like a whole car or a laptop. Because it's driven by market whims, it's continuous but highly stochastic, meaning it's super unpredictable and relies heavily on forecasting. But then we have dependent demand. This is for the components, the raw materials, and the subassemblies needed to actually build that final product. This kind of demand is lumpy. It's intermittent, spiking only when assembly actually happens. But here's the beautiful part. It's entirely deterministic. You don't guess, you calculate it directly from your bill of materials and your master production schedule.
And this brilliantly illustrates the exact difference. Picture a car factory. The independent demand for the cars themselves, that fluctuates. You might forecast you're going to sell 100 cars this week, but it's really just an educated guess. However, once you commit to producing those 100 cars, your dependent demand for tires is no longer a guess. It is a mathematical certainty. Every car needs 4 tires, so 100 cars means you need exactly 400 tires. You never forecast dependent demand, you calculate it.
Moving on to Section 2, the dependent demand problem, and exactly why traditional models just completely fail here.
Let me tell you, when production managers try to force the wrong models onto dependent demand, absolute chaos breaks out on the factory floor. I'm talking panicked supervisors, stalled assembly lines, and insane expedited shipping fees. Why? Because traditional models, like the economic order quantity or EOQ, are purely reactive. They're built for the smooth, continuous flow of independent demand. But dependent demand is lumpy. If you use a reactive model here, the system just freaks out. You end up triggering orders when you don't actually need them. Hello, massive overstock and huge holding costs. Or, even worse, because it's completely disconnected from the actual assembly schedule, you run into severe material shortages right when the line needs parts the most. The whole decoupling function breaks down. Bottom line, reactive models are totally misaligned with assembly schedules. We desperately need something proactive.
Which brings us to Section 3, the MRP solution for demand, a proactive, time-phased approach.
So, here is the hero of our story today, Material Requirement Planning, or MRP. It's specifically engineered to solve this exact dependent demand problem. What is it exactly? Well, MRP is a computerized, time-phased planning technique. Instead of just waiting around for inventory to drop to some arbitrary reorder point, MRP actively looks into the future. It uses this brilliant logic called backward scheduling. It looks at the due date of the final product and works backward, calculating the exact lead times of every single component to figure out precisely when an order needs to be released. This is exactly how MRP schedules dependent demand, by ensuring materials arrive exactly when they're needed. Not a day early to just sit in a warehouse gathering dust, and definitely not a day late to stall production.
Now, to make this powerful MRP engine actually run, we need 3 critical inputs. First up is the Master Production Schedule, or MPS. This is your what and when. What final products are we making, and when are they due? Second is the Bill of Materials, the BOM, which gives us the product structure and the exact component quantities we need. And third, we have the Inventory Status Records. This gives us the real-time data, what's already on hand, our lead times, and our lot sizing rules. But remember, and this is absolutely key, an MRP system is only as good as the accuracy of these 3 inputs. It is the ultimate example of garbage in, garbage out.
Let's walk through how this builds a logical, mathematical sequence step by step. First, we figure out our gross requirements. That's the total amount of a component we need based on the MPS. Next, we check our projected on-hand inventory to see what's already sitting in the warehouse. Subtract what we have from what we need, and boom, we get our net requirements. Finally, we offset that net requirement by the lead time, which gives us our planned order releases. That's the exact date we have to place the order so it shows up on time. It's a beautifully logical, backward-stepping dance.
Section 4, the crucial role of lot sizing, where we balance holding and setup costs.
Okay, so we know what we need and when we need it, but now we have to decide exactly how much to order at one single time. That's lot sizing. If we use a lot-for-lot approach, we just order exactly what our net requirement is for that specific period. This is awesome because it basically eliminates holding costs, but your setup costs are going to spike because you're constantly placing orders. It's perfect for a just-in-time environment, though. Then you have EOQ, which tries to find a balance, but often leaves you with annoying remnant inventory. Par period balancing is a neat heuristic that groups periods together until your setup and holding costs are roughly equal. But if you want the optimal, mathematically robust method, that's the Wagner-Witten algorithm. It uses dynamic programming to find the absolute lowest total cost across your entire planning horizon. Choosing the right method here directly impacts your company's bottom line. All right, Section 5, capacity validation via CRP. Bringing it back to reality on the factory floor? Because here's the thing. Everything we've talked about so far happens in a perfect, frictionless, mathematical world. But a real factory floor has physical limits. This is where a critical decoupling function happens in planning. See, MRP assumes you have infinite capacity. It might calculate that you need 500 hours of machine time next week and just happily assumes you have it. That's where capacity requirements planning, or CRP, steps in as your much-needed reality check. It takes those planned order releases from the MRP and tests them against the finite real-world capacity of your actual work centers. Basically, if MRP says build it, CRP asks, wait, do we actually have the machines and people to build it? And to figure that out, we calculate available capacity. The formula is pretty straightforward. You take the number of machines, or your labor count, multiply that by your working hours, multiply by the utility rate, and finally by efficiency. This specific calculation is the safety net that keeps your supply chain from completely breaking down. It tells you exactly how many standard hours of work a given station can truly handle before it turns into a massive bottleneck. Now, what's really interesting about this capacity profile is when you look at the periods over time. Notice the first period, we're sitting at an 80% load. We're totally fine there. But then, check out the massive spike in the second period. We're hitting 120%. CRP is waving a giant red flag here, warning us of dangerous overcapacity. If we don't fix this immediately, deliveries will absolutely be late. On the flip side, the third period shows a 60% load. That's undercapacity, meaning we're basically burning money on idle machines and idle workers. Section 6, Strategic Managerial Decisions. How we actually take concrete action based on all this data. So we've done all the math and we've spotted the bottlenecks. How do you, as an engineer or manager, use this data to make those high-stakes operational decisions? When CRP flags that 120% overcapacity, you have to issue action notices. And you've got a few strategic levers you can pull. You could try leveling the load by pre-building items, maybe move some of that work forward into a period where you only had an 80% load. You could add temporary capacity by authorizing overtime or maybe bringing on an extra shift. If that's still not enough, you might have to subcontract components to a third-party manufacturer. And if literally all else fails, you have to bite the bullet and reschedule the master production schedule itself. Managing this dynamic tension between material availability and facility constraints, that is exactly where you prove your worth as an industrial engineer. I want to wrap up today with a challenge to really test your systemic thinking. Imagine a sudden supply disruption happens. Say a major supplier just goes bankrupt overnight. How would you rebalance your MRP schedule and your CRP limits without halting the final assembly line? Think about that decoupling function, your safety stock, and all those strategic levers we just discussed. Because mastering MRP and CRP isn't just about the math. It's about having the agility to solve exactly this type of real-world crisis. Keep exploring, keep questioning everything, and I'll see you in the next session.